Hello, everyone. I'm Mike Booz, and this is Holly Dickson. We're with the Alaska Department of Fish and Game. We're the sport fish area managers based out of the Homer office. Today, we're going to do a presentation for you on what's going on with East Cook Inlet razor clams, kind of a up-to-date current status of East Cook Inlet razor clams since the sport fishery closure in 2015. Holly and I have been working a lot with razor clams through this transition and closure of the sport fishery, and have done a lot of the assessment work that you'll see here today. For many of you, the loss of this fishery has been a really big deal, and we're doing all that we can to ensure that we can identify a sustainable sport fishing opportunity with this resource. So let's jump in and get started. Kind of a quick outline of the presentation here. Holly's going to go through a timeline of the events that led up to the sport fishery closure for East Cook Inlet razor clams. And then we'll jump into our data collection and refinement of the methods and analyses that we're using to assess what's going on with East Cook Inlet razor clams. So we will also cover our stock assessment approach and the productivity indices that we're using to really assess what's going on. And then Holly will cover the future of our monitoring, and I'll go over the potential for the sport fishery reopening in East Cook Inlet.
All right, so to get started here, the timeline of events leading to the fishery closure. In the late 1950s, highway access from Anchorage down to the Kenai Peninsula was greatly improved. So non-locals, people besides Kenai Peninsula residents, could access these East Cook Inlet beaches. You can see the access points there on the map on the right, with Ninilchik and Clam Gulch being the two major ones. So the popularity of this fishery began to grow through the 1970s and all the way into the 1990s. In the mid-90s, the fishery reached the peak harvest and effort. So you can see that on this figure here on the bottom, the peak of the yellow dashed line and the green solid line, or the harvest and effort there. The blue solid line in the background is the CPUE, or the catch per unit effort. You can see that peaked slightly prior to the other two. And the best way to think about the CPUE is just that it's the number of clams a digger harvested on average when they went out to the beaches during that year. So you can see at the peak in the early 90s or late 80s, it was probably 39 or 40 clams per digger on average. After the mid-1990s into the mid-2000s, we started to see a decline in harvest and effort. Prior to that, it had remained at a pretty steady historical level since it reached the more popular level in the early 1970s. During this time, or slightly after, in the late 2000s, we also noticed the size and age composition of the razor clams in the harvest beginning to decline. So they were a bit smaller and younger all of a sudden. In 2010, there was a storm event with high surf that pounded the Ninilchik beaches and left a lot of adult clams dead on the substrate, unearthed from the sand. This is something we're asked about a lot, and it's just another event on the way to the closure of the East Cook Inlet sport fishery. The following year, we really doubled down on our abundance survey monitoring and other monitoring efforts that we're going to get into a little bit later. In particular, we started annual abundance surveys at Ninilchik South that year. So you can see that on this figure here. In 2011, the largest point there is that green triangle up at 1.6 million adult razor clams on the Ninilchik beach in 2011. That was actually the largest abundance we had ever estimated there compared to historical estimates since the late 1980s. You see we progressed with surveys through 2012 into 2013, where adults' abundances were severely declined on this beach. In 2013, we restricted the bag limit at Ninilchik South. In 2014, we restricted the bag limit on all East Cook Inlet beaches and closed the Ninilchik beaches to any harvest. And then in 2015, it's the first year all of the beaches were closed to any harvest by emergency order.
Okay, a quick summary of our historical monitoring and data sets. First, our primary data that we've had with East Cook Inlet razor clams has been effort and harvest data within the sport fishery, and this is beach specific. And on all of these beaches, we've also had a department collected age and length composition samples collected annually since the early 60s. And the intention of this data was to represent or mimic the harvest of the sport fishery that was occurring. Starting in the late 80s, we felt like we had a need to better understand what was going on with the harvest that was occurring in the sport fishery and how it related to abundance. And we started conducting periodic density sampling at both Clam Gulch and the Ninilchik beaches. Additionally to the sport fishery and abundance data, we also have some biological data that we've accumulated over time in the historical data. The first being size and age at maturity. This work primarily came from our department collected hand dug samples, but we've also had further analyses looking at the growth rates and the timing of spawning with graduate students.
Okay, so I'm going to get into the abundance surveys here to start and just explain our methods a little bit. This is an overhead drone video of one of our surveys. So I'll start it here and you'll see the fire hose with water coming out the end of the wand. So we put that in the substrate in these metal circular plots. And so within each plot, we emulsify the substrate until the clams float to the surface and the sand is completely liquefied. So we move out the beach, on a transect on a study grid that I'm going to explain next, emulsify the plots as we go, collect the clams. We have to move out with the tide and drag the fire hose up and down the beach with us. At the beginning of the shot, you could see a small boat sitting just out beyond the waves there with a water pump. And so we run the water pump to keep our survey going. Okay. So to start out with another visual here, this is an aerial image of part of the Clam Gulch beach. And so before we go out to do a survey, we draw our study area. And so we do that by drawing a line out at the water line and then a line at the gravel line. So the gravel line is the transition between the steep gravelly part of the beach right where it meets the flat sandy intertidal. So you can see that in the lower portion of this photo. So we draw the lines there and create a polygon between them. That's our study area. And so then we further divide this study area into 50-foot strips of beach or stratum. So we start at the gravel line and move out towards the water line with these stratum. Depending on the size of the beach, we can get all the way out to stratum 32. So once we have those drawn, then we'll go to this study area and we run a survey out on a transect line. So each of these lines of green dots is a different survey that we've done. Again, starting at the gravel line, moving out to the water line, and then moving back in with the tide. So we attempt to sample within each stratum as we go. I'll blow up the image here so you can see a little better. So here's a zoomed in image of what one of our surveys or transects actually looks like. You can see that within most of the stratum, we have 3 or more plots that we completed. Some of them are completely blank, and that's due usually to us trying to keep up with the tide as it moves out, or the tide catching us as we move back in. And then we'll pump anywhere between 3 to 7 plots in order to detect a clam before moving on. So this is what pumping pumping one of the plots looks like. You can see the metal ring there in the sand. The wand at the end of the fire hose is spraying water in. Someone's reaching in to grab a clam they probably saw floating on the surface there. And then in the GPS there is on a pole circled in blue. So we just mark or map our survey as we go. So after we emulsify a plot, we drag the metal ring through it. That's one of the ways we help to, filter all the clams out that might be floating in it. And then every clam we capture, we measure and age and enter the data as we move out the beach.
Okay, some important considerations of this abundance survey design and methodology. One is the amount of time that the sandy intertidal portion of the beach is exposed is limited to minus tide days. Typically, the beach is exposed for 5 continuous hours for us to work on, and there's only so many tides annually to work with. And so it's a pretty major limitation of the study design that we're only able to work on these beaches when they're exposed on the start of the outgo of the tide, on the minus tides, and as the tide is starting to come back in and flooding over top of these beaches. 2, the amount of sampling that we get is really limited, and so the whole beach strip and transects, that whole design is a study design that allows us to get a really good handle on what the density is on this beach overall across the length and the width of the beach with limited sampling. Another important consideration to know is that using a water pump to emulsify the substrate in these circular plots is really passive sampling technique. If you see that picture there with Holly and those clams outside of the bucket, almost all of the clams survive this process and are able to rebury themselves. Of course, the clams that we bump with the wand, there is some breakage, but very few clams are harmed in the process of doing this methodology.
All right, so we complete these surveys and we come back with this data and we have to actually estimate the abundance on these beaches. So how do we do that? Well, we do it by calculating the average density of each of the strata or the beach strips there that I showed you. So to do that, we start with taking the total number of clams that we captured and dividing it by the total number of plots that we pumped within each of those stratum on each transect. So here's a visual to help understand that. So here's one of the surveys again, and we're going to look specifically at strata 8. So if we blow this up and look with, let's say we captured 12 clams in strata 8 and we pumped 3 plots. So 12 clams divided by 3 plots would be 4 clams per plot, right? And so, but we're actually interested in not just how many clams per plot, but in the area. So we want to expand that to square meters. So each plot is a half a square meter. So that's pretty simple math, luckily. And we get 4 clams times 2 equals 8 clams per square meter. So now we have the density for one strata on one transect, but let's zoom out here. And so we're still looking at the same strata or the same beach strip, and we want to calculate the density at the other places that we sampled within that strata. So like, let's say at the top one, we just did that. We got 8 clams per square meter. And then at the next 2, we got a half clams per square meter and then 2 clams per square meter. So now we just need to average the densities for all within the same strata. So we'll just add those together, get 10.5 clams per square meter. Since we sampled within that strata 3 times, divide it by 3, and we get an average of 3.5 clams per square meter within that strata. So then the next step is to expand that to the actual area of that strata. So with this one, the strata happens to be just under 20,000 square meters. So 3.5 times that equals 69,867 clams. So that's our abundance estimate for one of the beach strips in that study area. So we just need to repeat that process for all of the other beach strips or strata on that beach. So here's a table showing the results of that for Ninilchik South in 2020. You can see each strata and then the density of that strata's area in square meters, and then the resulting abundance. Down at the bottom, the 331,000 clams is the adult razor clam abundance estimate.
Okay, some important considerations in the refinement of our abundance surveys to have more information for an improved stock assessment on what's going on with these Cook Inlet razor clams. The first thing that we did in 2011 was transitioned from periodic, less frequent abundance surveys at Ninilchik and Clam Gulch to consistent annual abundance surveys at Ninilchik starting in 2011 and Clam Gulch in 2014. This is really important to give us more information. The second thing that we did in addition to doing them every spring or every year is that we started to do them in the spring. The intention of this was to conduct all the surveys at one point in time quickly, so you have a very exact abundance estimate. And with it in the spring would be ideal prior to when most of the harvest would occur if the fishery was open. In addition to that, we've intensified our sampling. So on a beach like Ninilchik South, that's a mile long from the Ninilchik River to Deep Creek. Historically, we sampled 3 transects to estimate abundance, and now we're up to 6 transects with this. All of this sampling to be able to do this has really been through our collaboration with the Alaska Pacific University FAST Lab. And Professor Brad Harris bringing a small army of students and faculty down to support doing these spring abundance surveys. Something we always do in science is kind of look at trying to do it a little bit better. I won't get into the details of it, but we really have maximized our efficiency on the beach. We know where and when we're going to sample and improving the method with water pump and other equipment. And then another big thing that we've done is once we get clams in hand, and historically we just measured every clam. Now we're measuring and aging and collecting even more information from every clam. And all of this, like Holly showed you in the methods now, includes electronic data collection, which leads itself to an automated storage process, which quickly expedites the data from its raw format into an abundance estimate. And one important thing that we've also been doing is assessing the amount of razor clam habitat on our abundance survey beaches and refining the area estimates associated with it. Holly explained that we have a density estimate expanding to the total area. And so we've really spent time figuring out how much clam habitat is in each of those areas.
Okay, so I'm going to explain that habitat assessment a little bit more. One of the ways we've done it is to look at this high resolution aerial imagery. So this picture is a part of the Ninilchik South Beach. So we'll zoom in here a little bit and you can start to see that some of the habitat in this picture isn't hospitable to a razor clam. So the rocks in the upper left are really obvious. So razor clam can't live where those are. In the lower right part of this image is actually an exposed coal seam or coal bed. So without sand there, of course, a razor clam isn't going to be present either. So we put this imagery in ArcGIS and we draw out the bad habitat. It looks something like this. Anywhere a razor clam can't be, we'll draw it out, and then we overlay it over our study area. So you can see this is our study area of Ninilchik South. You can see our strata drawn there. The pink areas are bad habitat areas on this beach. And so then we subtract that bad habitat from that total area estimate of each strata so that we're not expanding our razor clam density to an area where there actually can't be razor clams.
Okay, really quick, the other primary data set that we have with the sport fishery close is those hand dug age and length samples that we collect. There's two components to these data. First is the collection in the field where we go out and hand dig mimicking harvesters. And then the second is the lab portion where we're actually measuring every annulus or growth ring on every razor clam that we collect. And so in the process of this, we didn't or haven't needed to improve this process much more than what it's already been historically. This has been a great data set, but we did refine it a bit. And the first thing that we did is just kind of standardize the annual collection date to mid-June. So year-to-year comparisons on things like average length are more standardized. We also have added in more people, again, with the APU Fast Lab. We just have access to having more help with doing these, and more crew has been beneficial because we have a variety of skilled diggers on these beaches to kind of better represent how harvest would have been occurring. And so we have people in these dig surveys that have never dug razor clams before to highly skilled diggers like Holly. So it's been a good change. And then lastly, we've just improved the way that we've looked at growth. Recently, the APU Fast Lab had a master's graduate student who dug into these data a little bit more substantially, which has been pretty beneficial. And so we've improved our analyses as well with it.
Okay, so we've looked at the couple of major data sets that we use, the abundance surveys and the age and length surveys. And so we're just going to talk a little bit about, what do we do with this data and what's our goal as managers. One of the things that we really know is that we don't know everything about these populations of razor clams on the East Cook Inlet beaches. We don't know, exactly where they come from, when they settle out of the water column. There's a lot of unknowns that are very difficult to study and that would be easier in some sort of other population of critters, like something that lives on land maybe, or a mammal, that you can observe in all of their life stages. So we're more concerned about what we can know. And so for us, that's mostly the births and the deaths and some of the growth going on in these populations. So this manager's approach to population dynamics is pretty simple. Let's say we start with a population of razor clams of a certain number. One of the things that's going to happen are the deaths. So without the fishery going on, this is all natural mortality. After this occurs each year, we're left with fewer razor clams, of course. But at the same time, there are razor clams that survive. And so those razor clams are growing and they become new adults and grow to the size of an adult clam that could be harvested in the fishery. So we have those. In addition to that, we have clams that were already adults and that survived. So those are our old adults. And then the other part of our population are our new baby clams every year that recruit onto the beaches. So we get those three parts of our clam population together. And if things are going well and the deaths were less than the new clams, we are back to the same number of clams or more.
Okay, taking that manager's approach to population dynamics and for East Cook Inlet, it's essentially just trying to understand how the numbers of clams on a given beach change, right? And so we have a desire to want to maintain a particular number of clams on these beaches so there's enough there to support a harvest opportunity annually. And so in that process, we've worked to develop a more refined stock assessment platform with the data that we collect and using productivity indices. I think in a lot of fisheries stock assessments, the typical approach is to model the data based on what you have. Things like mortality are estimated through modeling. Because we're managers and not just researchers, and we have had the ability to increase our sampling and change the methods ourselves, we've gone with a more empirical approach and actually have collected the data and improved the data analyses ourselves. So with that, thank you. At Ninilchik and Clam Gulch, we have the two primary data sets with the fishery closed. We have the abundance survey data and the age and length data from the hand dug samples. All right, you take those survey or data sets, you refine the methods and analyses, and you come up with these 9 productivity indices that we can use to assess what's going on at Ninilchik and Clam Gulch separately. Within the abundance survey, because the survey estimates abundance of both juvenile and adult clams, we have 3 indices within each of those: abundance, recruitment, and mortality. Within the age and length data, we have 3 components there as well: age, length, and then growth being a combination of the age and length data.
Okay, so we're going to start to get into some of the results of these different data analyses and surveys. So starting off with the abundances, I'm going to start with the Ninilchik South Beach and show you the abundances for both the juveniles and adults. The figure on the right is just a representation of the data in the table on the left. So starting with the juvenile abundances, from 1989 to 2012, which we're going to call our historical fishery level, the average annual juvenile abundance at this beach was about 250,000 razor clams. Since the fishery closure, the 2015 to 2020 period, that's increased to almost 900,000 juvenile razor clams on this beach annually. And then the adult razor clams. In the historical fishery, it was about 475,000 adult razor clams annually on this beach. And since the fishery closure, that's decreased to about 182,000. So you're going to see this same trend on the next 2 beaches I show you as well, with the juvenile abundances have increased quite a bit. And the adult abundances have not. They've remained fairly depressed. So the Ninilchik North Beach is a little bit different than the Ninilchik South Beach, despite their proximity to each other. But we start out with 1.1 million juvenile clams in the historical fishery period, and more recently we're at about 1.4 million. The adult razor clam population historically was close to 2 million annually, and since 2015 has been at about 700,000. And then our last beach that we are consistently surveying is Clam Gulch North. And so the juveniles there historically were at about 1.4 million. They've increased a lot to almost 6 million annually. You can see in the table there that in 2019, there was almost 13 million juvenile razor clams on that beach. The adult abundances historically were just over 2 million, and recently they've been very declined to just under 300,000 on average.
Another thing to think about with these abundance estimates, juvenile clams are really small clams. Adult clams are actually still pretty small. Those start at 80 millimeters or just over 3 inches, but those are the abundances that we're using to assess whether or not there's enough clams for the fishery. So that's an important distinction here between juvenile and adult razor clams. Okay, for both the juvenile and adult razor clams, we've also refined those 2 abundances to within life stages for both of them. But first, what we've noticed when we start digging into these data is that mini clams or clams under 30 millimeters are not really well represented in the abundance survey annually from one year to the next. And so we're not sure if we are not necessarily seeing those in the survey, that the sampling just doesn't detect them, or if these small razor clams are continuing to move. Either way, they're not fully recruited to the beach to a point where we can survey them. So they've been removed from those juvenile abundance estimates that Holly just showed you. So our juvenile size now is from 30 millimeters to under 80 millimeters. And within that, we've developed two size categories, a small and a pre-recruit. With the pre-recruit being the size of clam in this year that will then grow to an adult next year. And so these two size classes are established based on an assumed growth rate from one year to the next. And so that's done after the abundance survey, back after the data's been put together. The adult abundances have been changed to two life stages, a new adult and an old adult. New adults just being the clams that were pre-recruits the previous year and are now adult clams. So using these life stages is really an intermediate step to helping us look at recruitments of clams to the beach and juveniles and the recruitment of adult clams. And then it also helps us look at natural mortality. Here's a quick table of the abundances that are tweaked to its life stages. You can see in 2020, most importantly, that there are now 3.7 million pre-recruit juvenile clams at Clam Gulch North. So if they grow well and survive decently, there will be a significant increase in the abundance of adult clams at Clam Gulch beaches in 21.
Okay, so next up is natural mortality. So using the life stages that Mike was just talking about and using age composition of these clams, we can estimate the natural mortality that occurs each year for both juveniles and adults separately. So starting with the percent of juvenile clams that are dying of natural mortality each year, this table will have the Ninilchik South Beach and the Clam Gulch North Beach on there separately. So one thing to notice is that natural mortality tends to be less at Clam Gulch. The juveniles are surviving a bit better there in general than they do at Ninilchik South. The other thing is that Ninilchik juvenile mortality is highly variable. You can see some years it's down around 20%, and then other years as high as 75%. And then the last thing is it can be really different between the two beaches within the same year. So the best example of that is our most recent year. 71% of the juveniles died at Ninilchik South between 2019 and 2020, whereas only 21% did at Clam Gulch North in that year. So then looking at the same thing for adult razor clams, Ninilchik South is highly variable for adult clams as well. And then the other notable thing here, the most recent 2 winters were extremely high mortality on both beaches. Okay, and then just to look at it in figure form real quick with Ninilchik on the left and Clam Gulch on the right, the darker bars are the adults. I think, one thing to notice is that the dark bars are the adult natural mortality at Clam Gulch has been fairly poor in most years, whereas the juvenile natural mortality there has been okay or pretty good. Whereas at Ninilchik South, it's varied between whether juveniles or adults have fared better. The other thing to see is just the 2017-18 year. In 16-17 at Clam Gulch was really pretty good for both life stages of clams.
Natural mortality is a huge thing that's leading to the razor clams not recovering in East Cook Inlet. And so I'm guessing you're wondering first, what's causing this really high rate of clams leaving the beach naturally? And two, how is these rates that we're seeing here with these data compare to what it was historically? So historically, we didn't have the ability with the periodic abundance surveys to be able to estimate natural mortality. But based on the age composition of the hand dug samples that you'll see a little bit later, clams were reaching a more maximum age, which suggests that they were able to survive longer. So historically, natural mortality probably ranged somewhere between 20 and 30% annually for razor clams on these beaches. And so these rates that you see here are 2 to 3 times, maybe even 4 or 5 times in the really high years compared to that. So what causes razor clams to disappear at such high and alarming rates? Something that we're really interested in. I don't have complete answers for you, and we're going to continue to work at exploring those causes with collaborating with other scientists and our work with APU. Some of the things I think about are probably leading to that decline is, one is just the lack of habitat stability, or how habitat's changing on these beaches. That big winter storm event that we saw in late 2010 as an example of how habitat change can influence razor clam abundances. And so the more time we spend on these beaches, the more we noticed how sand is constantly moving and it's not always necessarily where it was before. And so if the sand's moving a lot, the critters that live in it are as well. And so, yeah, I think we need to pay close attention to how the habitat's changing. And second, an important thing to notice that's changed over time, particularly starting in the mid to late 2000s, was the expansion of sea otters in Cook Inlet, expanding their range from Kachemak Bay and Lower Cook Inlet up to these beaches in East Cook Inlet where razor clams are. And so razor clams are obviously a good food source for sea otters when sea otters are spending time in the Ninilchik or Clam Gulch areas, and they seem to be more prevalent now than they have been historically. We don't have any information on how much sea otters are using East Cook Inlet razor clams, but again, it's something we want to work with other scientists here in the Homer area to better explore and understand. Okay, recruitment for productivity indices, both juveniles and adults. Start with the juvenile recruits. Again, remember that I said that clams 30 millimeters or under, those are so small that the abundance survey struggles to detect them consistently. And so what we look at for assessing juvenile recruitment is the first cohort of a size that we know is fully recruited to the beach. And so what you see when you look at the data in these tables is that recruitment is highly variable from one year to the next, and it can change by a 10 or 12-fold increase. Ninilchik ranging all the way from just a few thousand to 2.3 million in these years that we've been looking at. Juvenile recruitment's a really important part of the rebuilding process. You can't increase the number of clams that you have on these beaches without getting new little clams to come in. Another thing that you notice is that recruitment between the beaches annually can be really different. For example, here in 2019 that Holly just highlighted for us, the juvenile recruitment at Ninilchik South was well below average that year. Meanwhile, at Clam Gulch, it's the highest that we've ever seen. Adult recruitment, again, is that movement from the juvenile pre-recruit life stage to the new adult life stage. Adult recruits also have been highly variable at Ninilchik, and as low as just a few thousand in 2016. Really hard to have any fishing opportunity when you have so few adult recruits moving into that adult size. So this has also been a pretty big limitation on why the fishery is remaining closed, because the number of adult recruits that we're seeing annually is not enough to even compensate for the natural mortality rates that Holly went over, let alone be enough to provide harvest opportunity or to replace the harvest that would have occurred.
I think one thing to note here, that Mike just mentioned, the recruits haven't been sufficient to replace harvest, and the historical data prior to 2011 isn't up here. But one thing I'll show you a little bit later too is the Ninilchik recruitment comes in large pulses. Large cohort will recruit onto the beach every 2 to 4 years, and then that will did carry the fishery harvest. In contrast to that, at Clam Gulch, they had pretty consistent, good annual recruitment, during the bulk of the fishery years. And so in those years, for every one clam that was harvested, there was about 10 to 20 clams that recruited to the beach to replace that particular clam. Okay, so moving on to age and length here, another productivity indice that we're using to gauge the health of this razor clam stock. You can see in this table shows the average total length of razor clams at each of these beaches. So if we're looking at this, in a table with each annual average listed out there, you'd see that through the fishery all the way until 2005, the average total length of these razor clams was pretty steady. And then as right after 2005, it began to decline. And it's continued to do so, through the 2000s, and after the fishery closure in 2015, it's continued to decline through 2020. The most recent period there, 2015 to 2020, the average total length is really pretty small, 83 and 73. That's about 3 inches. And at Clam Gulch, the average clam there is actually a juvenile sized clam. It's not even quite an adult. Just for reference, the historic average size there of 119 or about 120 millimeters is about 5 inches. Okay, and then this figure here shows the age composition of razor clams at the Ninilchik Beach. So to look at this best, and look at each year as a column there. So here we're looking at 1991, and you can see that the largest bubble there is lined up on age 3. So that means that the majority of the clams on the beach that year were 3-year-old clams. You go to the next year, 1992, and you see the largest bubbles on age 4. So age 4 comprised the majority of the harvest, or the majority of the clams on the beach that year. This lends itself to showing what I was talking about when I said, there was a large recruitment every 2 to 4 years. You see that cohort of clams moving through at each, successive age as we go on here. The other thing to see on this figure is the maximum age through 2005 was greater than 10 years old, with plenty of clams there at 12, 13, or 14 years old even. And then after 2005, that abruptly declined and hasn't recovered since. So this is what Mike was talking about earlier with the natural mortality as well. If you take the same number of clams and apply a natural mortality rate of 75% of them dying each year, they're only going to reach so high of a maximum age, right? So we see here since 2005, they really haven't been getting older than 7 or 8 years old. And we know that these natural mortality rates have been high. So if we look back to years prior to 2005, and take, the same number of clams, you'd have to assume that the natural mortality rate would be more like 20 or 30% for them to reach a maximum age of 12 or 13 years old.
Thinking about these data, it's great perspective to put into the amount of data that we actually have. I mean, going back to the 60s gives a lot of historical perspective with these. The other important thing to remember is that these are dug on a whole bunch of beaches. I think there's 10 beaches that we're annually collecting size and age composition data from. So although our primary way to decide if there's enough razor clams available to support harvest is from our adult abundances from the abundance survey, the age and length composition data is collected on all of the beaches or 10 beaches throughout all these Cook Inlet. And that really gives us some perspective on what's going on, or a snapshot of what's going on more than just these small, little, intense abundance survey beaches. And so this trend that we saw from the early 2000s to now, where there's no more old clams, that's something that we've seen on all of the beaches that we survey for age and length data. And so Holly here has presented the abundances on Ninilchik beaches where they were most heavily harvested. And with having these data on beaches that were both moderately harvested, like Clam Gulch, or lightly harvested beaches in between Ninilchik and Clam Gulch, where diggers rarely went, we can see that the same trend occurred regardless of the harvest rate. And so that's given us some historical perspective on the potential effects of the sport fishery onto these compositions that we're seeing here. And so we feel pretty confident, based on how these compositions have changed on all of the beaches, regardless of harvest level, that harvest wasn't really the thing that led to the decline of East Cook Inlet razor clams. Oh, okay, growth is just the combination of age and length data together. And I mentioned the graduate student from APU's kind of dug into this more recently. But what we've done is taken it one step further and really wanted to, as a productivity indice, was to look at growth on an annual basis. And so to do that, instead of looking at the size at age, we looked at the growth increment from 1 year to the next on all of our clams. And what we've seen when we've done that is that growth is actually highly variable from 1 year to the next. But most importantly, on this graph over here, there's a lot going on with it, but I just want to kind of clue you into 2017 and 2018, where these little mounds that you see lined up with their color-coded bar, that's the average of all of those. You can see that the average size is well below its historical average in 17 and 18. And so growth was really poor in these years for all age classes on all beaches. And so this is just another way of looking at how well the stock is doing. And it looks like in 2017 and 2018, growth has definitely influenced their ability to grow into the adult size.
So all of these productivity indices that we are talking about are related to each other in some way. So in particular, this growth indice is going to affect the recruitment to the adult size, right? If these clams are growing really slowly, they're going to fail to reach the adult size as well, or as soon as they used to. So this figure just shows age 3 Ninilchik clams in blue, and then the age 4 Clam Gulch clams in purple. So you can see that, while it wasn't 100% historically, it was the majority of those clams of that age at those beaches reached the adult size by the time they were that age. Of course, with the exception of the Clam Gulch clams there in early 2000, where they also had a really poor period of growth. But then, looking to the most recent cohorts of clams here, you can see that, since 2012 or 2013, essentially 0% of the clams of this age or reaching the adult size of these beaches. It's just taking them longer and longer to grow to a size that would be harvestable in the fishery. And at the same time as that, they're experiencing high rates of natural mortality along the way as it takes them longer to get there.
Okay, so we've shown you the data with the 9 productivity indices that we're using to do the stock assessment. But here's a slide on basically a more qualitative assessment of these data in a color-coded report card. Just a more quick glance at how well razor clams performed annually. So if things were really good with all of these indices, it would mostly be greens and maybe a little bit of yellows. I think what you're primarily seeing here is that although there are some greens, they're primarily reds at Ninilchik. And so looking at Ninilchik compared to Clam Gulch here, you see some differences in just the color coding. So what's going on with juvenile clams at Clam Gulch is seemingly pretty good. And that's what we want to see. And that's a good start to the recovery of razor clams there. Though the adults are much severely worse than Ninilchik. I think that's about to change based on those pre-recruits. And then the age and length data based on the growth, and the survival, those haven't been very good at either location.
Okay, so to start wrapping up here, our future monitoring, we'll continue to do our annual abundance surveys at both the Ninilchik beaches and Clam Gulch North, or continue our habitat assessment. In particular, something new we're working on is working with this digital elevation model of the beaches. And so there's an image of it there. I guess each color strip there is a different elevation on the beach. So you can see where they're really close together is the steep gravelly part, and then they get wider and more spread out. It's the flat sandy part. So we're looking at post-stratifying our abundance estimates to look at abundance by elevation on the beach, or you could think of it as abundance by negative tide level, I guess, rather than looking at it in those 50-foot wide beach strips that I was showing you earlier. We're also going to continue our age and length surveys to continue that large data set. And if the fishery reopens, we'll be doing harvest monitoring on the beaches. So we'll be there counting diggers and then interviewing diggers as they leave the beach and counting clams in their buckets. And then lastly, we'll continue our collaborations with our really growing list of partners here. But, most importantly, most significantly, the APU FAST Lab has contributed with many of these studies. So, looking at a lot of different stuff, but the genetic connectivity of the different beaches, looking at whether disease or microplastics are an issue in these stocks, and then gene transcription and other environmental drivers that could be influencing things. Okay, the big question, when will the sport fishery reopen for razor clams in East Cook Inlet? First, I think acknowledging back to that report card, if things were improved to a point where they were fully recovered, or to the productivity level that we've seen historically, it would mostly be greens and some yellows. And so we know we're not there, and we haven't been there for quite some time. And so the thought of the fishery reopening to what it has been historically seems pretty far away right now. I don't think we want to give up the optimism that this stock can be as productive as it once was, and we know that it can be, but it's been a long time since we've seen it be that productive. Obviously some good signs with some really strong recruitment of juvenile cohorts in the last few years, but it's not enough given the natural mortality rates and the poor growth that we've seen. So we've been spending a lot of time thinking about
developing a more limited harvest opportunity that could occur for everyone to get a chance to go and dig some razor clams that would also still allow people, yeah, that small chance to go, but at the same time, allow razor clams to rebuild on these beaches. And so what we've done is we've drafted a proposal to the Alaska Board of Fish to implement a management plan for East Cook Inlet razor clams. If adopted, this management plan would break the East Cook Inlet beach into two management areas, one for Clam Gulch and one for Ninilchik. I think with the data that we've shown you in this presentation, that the productivity of clams in these two areas are really different. And there is a potential to have a fishery in one location while the other is not. So this proposal that we have was scheduled to be deliberated at the statewide miscellaneous shellfish meeting that was for this March. That's been postponed due to concerns with COVID. It hasn't been rescheduled yet, but will likely happen either later this year or early next year. But that proposal, if you want to take a look at this management plan proposal, is on the Board of Fish website right now. It's proposal number 257. And it's open for public comment that you can provide in written form online with their form. So I would encourage everyone that's really interested in razor clams to go take a look at that proposal and think about trying to contribute to it. So the nuts and bolts of that proposal is taking the fishery and splitting it into the two management areas, like I said, and then also having two fisheries within each area, one being a more limited fishery that would provide a small harvest opportunity, and the other one being the historical fishery. So with those two fisheries, what we've suggested is to identify abundance thresholds in both areas for both fisheries. Right. And so there's a minimum number of razor clams necessary to trigger a fishery in both of these places. We've also incorporated the use of those productivity indices that we've gone over here with you into it. So those things are considered on whether or not the fishery has returned to its historical productivity and can support more harvest opportunity. We've also tried to suggest what is an appropriate harvest rate for both this more limited harvest opportunity and the historical fishery. And then we've taken a shot at what the season and bag limit should be associated with this more limited harvest opportunity. Okay, with that, we'll wrap up here and take a shot at answering any questions. Thanks everyone for tuning in.
Yeah, thanks everybody. And if we don't get to your question or you have more later, feel free to reach out to us at the Homer office. We're happy to talk about razor clams.